Picture this. Back in the day, you would visit Madame Zaza, peering into her crystal ball, hoping for a glimpse into your future. Her predictions were all about intuition, guesswork, and a little bit of luck. Fast forward to today, and instead of crystal balls, we got AI and machine learning doing the heavy lifting for our predictions. So, how is Madame Zaza's crystal ball, our stand in for traditional software, different from AI? Alright, let's break it down. Traditional software. Think of it like Madame Zaza's crystal ball. It only shows you what it's been told to show. It follows a strict set of rules, step by step, doing exactly what it's been programmed to do. No surprises, no creativity, just predefined actions. Examples? Classic stuff like Word, Excel, web browsers, calculators, or even early video games like Tetris or Super Mario, where every move is hard coded into the system. It's reliable but rigid. On the other hand, AI is a whole new ball game. Imagine a crystal ball that just doesn't spit out the same old predictions. It gets smarter every time it gives you an answer. AI learns, adapts, evolves based on the data it's fed. In tech speak, AI refers to machines performing tasks that usually require human intelligence, like decision making, problem solving, or even understanding natural language. Think of chatbots like Siri or Alexa, where it sets reminders or play music based on your voice commands, or robots in factories assembling products with precision. AI can handle anything from simple rules to complex evolving tasks. But here's where it gets really interesting. Enter machine learning. This is where things start feel like more futuristic. ML is a subset of AI. It's all about computers learning from data without being explicitly programmed for every little task. For example, Netflix doesn't just offer random shows. It learns from what you have watched to recommend what you probably would enjoy next. Or your email spam filter, where it learns from past patterns to block junk before it hits your inbox. Now let's roll up our sleeves and dive deeper. What's really going under the hood with ML driven systems versus non ML driven systems? Let's take a closer look. In simple terms, with traditional software, you tell the computer exactly what to do. With machine learning, we teach the computer how to figure things out on its own using the data we give it. Instead of hard coding all these rules, we let the machine learn patterns and make decisions based on what it's learned. For example, imagine trying to forecast the weather with hundreds of different factors like temperature, humidity, wind speed, and so on. Instead of manually figuring out how all of these factors are related, you can feed historical weather data into the machine learning model, and it will learn the patterns and come up with its own rules to predict the future. Pretty cool, right? But here's the key question. What kind of data does the machine need to learn effectively in an enterprise setting? In an enterprise application, having your data ready is like fueling rockets for launch. Machine learning models thrive on diverse data and are shaped by the problem they're designed to solve. Whether it's images, videos, text, or structured business data, it's not just about having data, it's about having clean, well organized, and properly labeled data. Without that, your rocket might never leave the ground. Let's dive into the key steps of data preparations that enterprises need to put in place and why this foundation is crucial for successful machine learning deployments. Let's now break down the key factors for getting your data ready for machine learning, because no one wants the data to be a mess. First up, data location. First, you need to know where your data lives. If it's scattered across several servers, databases, or cloud storage, it's like trying to find your keys in a messy house. Organizing your data is essential for smooth machine learning operations. No one wants to be stuck with data puddles everywhere. Data quantity. When it comes to machine learning, size does matter. The more data you have, the better your model will be at spotting patterns. Think of it like trying to learn a language. You will pick it up faster if you hear lots of examples. So get those data buckets filled up. Next up, data security. Protecting your data is non-negotiable, especially when it's sensitive. Whether it's your personal information or business secrets, security is the key. No one wants to turn their customers into toads. Keep that data safe. Next up, data diversity. It's not just about having a lots of data. It's about having the right mix of data. If you're only feeding your model one type of data, it's like feeding a dog the same kibble every day. It gets boring fast, really fast, and your model won't learn as well. So mix it up. And finally, data quality. Quantity and diversity are great, but if your data is messy, it's like trying to bake a cake with expired ingredients. Clean, accurate data is what makes your model work well. Remember, garbage in, garbage out. So keep that data fresh. In the end, you want your data to be more than just a collection of puddles. It should be clean, organized ocean that powers your machine learning rocket. Now that you covered the importance of getting your data ready, let's dive into how traditional machine learning uses the data to make predictions. In traditional machine learning, we train models to recognize patterns in data and predict outcomes based on those patterns. It's kind of like giving the model a bunch of examples and letting it learn the rules by itself. Once it figures out the pattern, it can make predictions on new data. Here's how it works. Let's use ice cream sales plot as an example. Training the model. We feed the model historical data. In this case, past temperatures and corresponding ice cream sales for two groups, kids and adults. The data points for kids, which are blue circles in the plot, and adults, green crosses, represent the actual sales numbers at different temperatures. The model takes all of this data and start to analyze its patterns. How do they learn the patterns? As the model studies the data, it learns the higher temperatures generally lead to more ice cream sales, but for both kids and adults. It uses this relationship to come up with a formula represented by the red line and describes how sales are expected to change with temperature. The key here is that the model doesn't just memorize the data, it finds the underlying pattern so it can apply it to new situations. And how does it make the predictions? Once the model has learned this pattern, it can use it to predict the future sales based on the temperature it has never seen before. For example, if the temperature tomorrow is 92 degrees Fahrenheit, the model can predict how much ice cream will be sold to both the kids and adults. The red line represents the model's best guess at what sales will be based on the temperature. Dealing with more complexity, this process can get more complex when you introduce more variables. For example, we can add factors like humidity, time of the day, or whether it's a weekend or a weekday. The model can take into account when making these predictions. This flexibility is what makes machine learning so powerful. It can handle variables and learn from them simultaneously. The algorithm used here is called linear regression, which is one of the simplest and most common machine learning techniques. It works by fitting a straight line through different data points that minimizes the error that the actual sales and predicted sales. In this case, the model doesn't treat kids and adults differently in terms of learning the pattern. More complex models like decision trees, random forests, etc. are available that might handle both the groups separately. Congratulations! We just covered a class of models called supervised regression. Now that we have seen how the model learns patterns and makes predictions, it's time to connect the dots. Just like the turkey on this slide, regression models use past data to predict the future outcomes. The turkey predicts steady weight gain based on previous trends, assuming everything will continue smoothly into December. But what it doesn't know is that Thanksgiving is coming and that the growth pattern might hit an abrupt stop. This reminds us of something important about supervised learning. It works great when things stay predictable. but it can miss those unexpected changes, just like our earlier ice cream sales example. Remember that ice cream sales model? If that model has only seen sunny days, it might predict more sales as temperature rises. But what if we suddenly have a rainy day? Without that rainy day data, the model might keep predicting high sales, just like the turkey steady weight gain prediction. In both the cases, the model prediction would miss a key factor: rain for the ice cream sales or Thanksgiving for the turkey. The lesson here: supervised regression models rely on the data they are trained on, and unexpected events can throw them off if they are not part of the training data. Now that we have covered linear regression, let's move on to another type of algorithm. Just like before, we use data to train the model to make predictions. However, instead of predicting continuous values like sales amounts, this algorithm is used to predict binary outcomes. In this case, whether someone will buy ice cream or not. Here's how it works. Use our ice cream sales example. We feed the model historical data, temperatures, and whether kids, blue circles, or adults, green crosses, bought an ice cream, 1 for yes and 0 for no. The model takes all the data and starts analyzing it to understand the relationship between temperature and likelihood of buying ice cream. The model learns that as the temperature rises, the chance of someone buying the ice cream increase. It doesn't just memorize the data, it learns the underlying pattern and maps out the probability of purchase at a given temperature. The red curve shows this. It's the model's best guess of the probability of buying an ice cream as the temperature change. Once the model has learned the pattern, it can now make predictions about new unseen temperatures. For example, if tomorrow's temperature is 85 degrees Fahrenheit, the model can predict the probability that both kids and adults will buy ice cream. The red curve shows that the likelihood of buying ice cream increase as the temperature goes up. To deal with more complexity, this model combines the data of both the kids and adults into one prediction. But just like with linear regression, the process can get more complex. If you want to include more variables like humidity, time of the day, or special events, we could build more sophisticated models to handle these two variables, improving the accuracy of our predictions. The type of the algorithm you use for predicting binary outcomes like yes or no, or to buy or not to buy. In this case, the model combines data of both the kids and adults to predict the probability of buying ice cream based on temperature. If we needed to separate these two groups, more advanced models like decision trees or random forests could handle it. With this approach, we are not just predicting a number, but the likelihood of an event happening based on the patterns we have learned from the data. We just addressed another class of models, supervised classification. And what better way to explain it than Santa's annual classification system? Naughty, nice, or neutral? Just like Santa on this slide, classification models use labeled data from the past to predict which category a new input, in this case the child, belongs to. Santa's decisions are based on past observations. Has the child been good, bad, or somewhere in between? This reminds us of an important point about supervised classification. It's all about sorting new data into predefined categories based on patterns learned from labeled examples. Remember our earlier ice cream sales example? That was a binary classification problem. Yes or no to buying an ice cream. But classification can involve more categories like Santa's naughty, nice, or neutral. Just like Santa relies on past behavior to classify kids, supervised models relied on past data to make decisions. And that's why it's called supervised. The lesson here: whether you're a kid visiting Santa or data entering a machine learning model, the principle is the same. Learn patterns, determine the category.